Hello? Testing, testing. Room to order of the universe. Hi, everyone. I hope you're having a great night. I'm Darshan Swartbelly, and this is the Star Eyes Initiative. We're going to start off with a set of originals, well, really two originals, written by me, followed by a song that is basically the... You know what? We're going to switch it around. We're going to start with this song because it's going to set the mood of which is orbits. We're going to be focusing on our orbits today. The first one is a song literally titled Orbits by the great and late Wayne Shorter. And that is going to be completely improvised. Yeah, Wayne was one that really enjoyed and talked about the universe through his voice, his musical voice. We're going to follow that up with a song entitled Dance with the Black Holes, which basically describes the dance of two binaries, or a system of black holes that are a binary pair that go from an in-spiral somewhat far away from each other until they eventually merge. And it also happens that this song and the next song are directly related to work that has been done at Sierra. So, I mean, Sierra is well known for having done a lot of gravitational wave research. So, first one is kind of an ode to that. And then the second one you'll hear, which I've called One Hot Jupiter Over Easy, Please. That is about the dynamics of a Jupiter-sized planet that is still kind of a mystery. We don't know the exact answer yet. To why this planet as big as Jupiter, goes from the very edges of the disk that forms planets in what is, the baby steps of a solar system, to go really, really close to its host star, giving it the name Hot Jupiter. And we'll basically go from the beginning of that molecular cloud which creates this solar system to somewhat exploring mechanism that takes it to the star. With that, let's get to it. hope you heard the Black Hole Stance and merch. Hopefully. But if not, there's a video up there somewhere that has a performance of this where we actually go through the entire thing step by step. So check that one out. And we'll do the same for what school we're about to play. So this one's for Hot Jupiter. Nick? It's all you? Oh, I guess, I don't know. They're both trumpet players. We've never done this before. Give it up again for the rest of the band. Thanks.
Thank you to the band. Thank you so much. And thank you to everybody who's here with us tonight as Northwestern's homecoming weekend is getting started. I also want to thank the alumni of Northwestern University who support our lecture series, annual public lecture series, for a few years now, several years, and we are very grateful to have your partnership. I also want to thank all our staff and students and postdocs who are out there and inside this room who have helped to make this event possible. But I'm excited this particular evening to welcome you all because it is a special evening. We're marking 15 years anniversary of this Interdisciplinary Research Center for Astrophysics. It's been an amazing ride. My name is Vicky Calogera. I'm the Sierra director, the center I'm talking about, and a professor in physics and astronomy at Northwestern. In 2009, I was given this amazing opportunity to launch Sierra. And of course, I had no idea what would happen over the next 50 years and where we would find ourselves at present. We started on a long history. Let me see if I can control the slides. We started on a long history back in Dearborn Observatory, an observatory which has a historic telescope connected to the discovery of white dwarfs, and even Hubble's discovery. And that fall in 2009, we had certain plans in mind, but we never expected that we would find ourselves now being at the forefront of our field and competing with the best peers from our colleagues and other universities. We are driven to study the universe, which changes slowly over human timescales. But our understanding of our universe can change dramatically during our lifetime. And of course, Sierra changed dramatically in our 15-year-long history. Now, how did we do this in only 15 years? Well, Sierra is not just a research center for astronomy. We focus on exploring astronomy's connections with fundamental disciplines, disciplines of fundamental science, engineering through instrumentation development, and now AI, but also arts and humanities. And what you saw today and what you're going to hear from the public lecture from our speaker is a bright example of these partnerships that are not common. We also, through successful competitions and strategic investment, we get access to the most advanced telescopes in the world. And that has also changed how we do our work and how we pursue discoveries. And for the first time in Northwestern's history, we are aiming now to become construction partners in the Giant Magellan Telescope, which is an engineering marvel powered not exclusively, but powered wholly by AI. Now, all you heard is what we do. But of course, none of this can happen if we don't have the people who do it. So Sierra takes a people-centric, holistic training approach for our research and education. And we realize that our graduates and our postdoctoral fellows are graduating and leaving Sierra and pursuing careers not only in academia, but also in industry, nonprofits, and government organizations throughout STEM. Furthermore, we focus and engage with you through events like this and a plethora of other events, but also we focus on our local communities, and we partner with students, and we partner with teachers in our schools to make sure we invest in our future. We also, looking back at our 15 years, we have made press-worthy discoveries that start from our sun, exploding stars, black holes, and the galaxies. And over this 15-year period, we have reached and connected through these discoveries with over 750 million people around the world and brought Northwestern's name to them. Looking forward in 15 years, who knows where we're going to be? We're looking forward to that future. We will continue focusing on interdisciplinary exploration, training highly skilled people who will go out and impact the world. We hope you will join us on this journey. Now, looking forward to tonight, I'm going to tell you about our special speaker. We're very grateful to have him with us tonight. Professor Stefan Alexander from Brown University is joining us tonight. He's a theoretical physicist and a cosmologist, and he works at the intersections of quantum gravity and particle physics. He's also a musician, and he's also a book author. He was born in Trinidad and grew up in the Bronx. He started his academic career as an undergraduate at Haverford College, where he studied physics. And he did his PhD in physics at Brown University, and then postdoctoral work at Imperial College of London, Stanford, became a professor first at Penn State University, and then moved to his home, Brown University. He has served the community in many different roles. He has been the president of the National Society of Black Physicists, and he's renowned not only for his work, but also for his work at for his research, but also for his work at the intersection of science and society. For many years, he has led programs that bring students to connect to science through music and music technology. And at present, he runs a program in downtown Manhattan that brings students from all around Manhattan to the center to connect with scientists and learn about science, but also learn about music and how music and physics and other sciences connect together. He also authored multiple books, but the focus of the lectures is the jazz of physics. And remember, if you fill in the survey on your way out, then you have an opportunity to get a signed copy of his book. Without further ado, please help me welcome Professor Stefan Alexander.
Hello, everyone. While we're being set up here, it's a real honor. And I first want to thank Professor Vicky, as I joke, we call her Vicky. You know, she doesn't know this, but she was one of my heroes as I was growing up in physics. I mean, as a colleague, you know, just watching her work bloom and all the amazing things that she has done here at Northwestern with Sierra. It's really taken Northwestern all over the globe. And let's say, I hope we can do the same thing for my institution. All right, so there's a lot I'm going to cover, but you know, in the interest of time, there are going to be some things that I probably won't cover because I'm, you know, dealing with a lot of things here. So what's the word jazz and physics? People say, what do these two words have to do with each other? Why are they together? But this is really more a story. It's my story. It's a story of a kid growing up in the Bronx, New York, trying to find my way through life. And unfortunately or fortunately, it was an improvisational life, as many of our lives are. And in fact, you can say, well, what does jazz have to do with physics or the universe? Well, I think my claim is that the ultimate improvisational system is the universe, and we are being played by it, okay? And that's not a joke. I mean, like, you know, I have friends that are like, they live in caves and they meditate like for years and things like that. And I do actually have a friend like that. And, actually, he's from Michigan, moved to, he's now the Dalai Lama's doctor. So as a kid, I was growing up, you know, and I grew up in a musical family. You know, at some point I might, should I take this jacket off? And at some point I might, it's kind of warm. And when I get a chance, I might need some water. You know, when I was a kid, I was, how do I put it? There were certain, I don't know, the cool kids did music and the nerds did science. And I was kind of in between. And so there was also a conflict about what should I do. And, you know, of course, growing up in the Bronx in the 80s, hip hop was a thing. In fact, hip hop was created in the Bronx around the time when I was growing up. And so, so obviously what would you do? You would seek your, if you were a closet nerd, you would seek that out from maybe the hip hop artist. And in fact, where's my hip hop artist guy? I guess it's not here. All right. But okay, this is the hip hop artist. This is John Coltrane. And Coltrane was somebody I was introduced to as a high school student. My high school physics teacher was also a saxophone player. And he introduced me to the music of John Coltrane. And as I started reading about him, and later on I realized, I learned that this is actually a hand drawing of Coltrane. Coltrane was, went beyond just the jazz repertoire of music. He was an explorer. He really believed that music, he could like change people, change the world. And he turned out that everything he can get his hands on about Albert Einstein, he would read it. And so this is, and we'll get back to this diagram. So as a person that was trying to, you know, find my way as a, you know, as a person maybe pursuing music or pursuing the sciences, this Coltrane inspired me that maybe it's okay to not be inside of a box. All right, so he was definitely an explorer. Another influence that really, person that influenced me was Albert Einstein. So not only was Albert Einstein just probably one of the greatest scientists of all time, but he, as you know, whenever you get stuck in a problem, oh, I don't need a mic. Whenever Albert Einstein would get stuck in a problem, he would go off to a piano and improvise until some new idea came to him. He was known as a violinist for his sound. He was very serious about his violin. And most importantly, Albert Einstein wore his personality on his sleeves. He didn't really, this, whatever notion you had about what a scientist should be like and act like, Albert Einstein just, he rode a bike and had his tongue out and that kind of stuff. But now what I want to do is to say that I want to take us back to the very birth of what we call Western science. So we're going back to around 500 BC, all right? So run the clock back 2,400 years plus 500 years, all right? And we bring ourselves to the Pythagoreans, who, you know, from the island of Samos, which is where, not from Greece, where modern day Greece. So I have to, you know, pay homage to that. So what I want to do now is to sort of talk about this. What the Pythagoreans were trying to do was understand the cosmos, the motion of the planet. In fact, the word cosmos meant that which gave order to the universe. And I believe that word was created by the Pythagoreans themselves. And I have someone here that will probably translate and tell me that that's correct. But what did they discover? They believed that the planets were playing a harmony, actually, in integer ratios to their orbits. And so the universe was sound. And in fact, this is the idea of what you probably heard of as music of the spheres. So Pythagoras wanted to actually experiment with this idea. And this is an instrument, and my saxophone will serve as this instrument on the board. And so what I'll do is actually demonstrate what he was trying to do. Integers, right? So 1, 2, 3, 4. And basically, so if I take, if 1 corresponds to the first big wave up there, except I close all the notes here. And if I half that note, that's 2. What would the other one be? That would be the octave. If I go up 2/3, which is 1/3 or 2/3, that would be. Right? So that's the fifth. That's the fifth. So basically, what he discovered by trying to understand music of the spirits was now what these musicians were playing, which is our so-called musical scale.
Turn on your mic.
Huh?
The box.
Oh, my mic. That explains why I was speaking so loud. Can you hear me?
Because the live stream cannot hear you.
Oh, no. There's a mic on now.
Yeah.
Okay, sorry about that. So basically, our Western musical scale system was actually invented, not just a Pythagorean theorem, by Pythagoras. But it came about by trying to understand the music of the spheres. So that's the first. Now this led his students, his followers, Plato, Aristotle, Copernicus, all these were followers of the Pythagoreans. And they went off trying to understand now these planets in terms of what they call all is number, right? So the mathematical systems and the geometrical systems to understand the motion of the planets, and this, what we now know as physics, came about from the birth of music and science at the same time. That's the first interest. In fact, like how the heck he's not? Well, when I was a professor at Dartmouth College, I taught a class with a historian of science where we trace the entire history of physics, and it begins with this. So I'm kind of compressing this entire year-long class, semester-long class in 1 hour. Okay. So I want you to pay attention to these wave-like patterns, because this will come back later on as we think about our modern universe. That's kind of where I'm going at. Right? I want to talk about, so I've kind of introduced you to the basic building blocks of music, which are these tones, these notes, which actually have to do with these numbers, which then, according to the Pythagoreans, might have to do with the planets or the universe. But then that system failed, actually. Fast forward 2,000 years, many, many smart human beings, and we can go off with a laundry list of people, but central to this is Ptolemy and the alchemists. These were systems that were based on, okay, we have these perfect circular orbits, all these planets, and it got a little complicated, and it wasn't working. And then Kepler came on the scene in the 1600s. And what Kepler did was he threw all of that away because it didn't work, and he returned back to the Pythagoreans. What did he do? Well, he basically took data, which was known at the time, and was able to map or relate the speeds of the planets, he had that information, to musical notes by taking ratios, the same ratios that I did here. He took Pythagoras' idea seriously, and he wrote down musical notes, see, for the planets. This is his own handwriting here. This is from his book, Harmonies, Music, whatever. It's some Latin word that I don't pronounce. Harmonies of the World. And there it goes. And so what he figured out from this, that it made no sense. Give up, run away, because what he found was not any kind of harmony, he found dissonance. And in fact, if you play Earth, this is Terra, it's very dissonant, actually. And he had a very difficult life, actually. His mother was almost burned to the stake in the witch trials of Germany. He lost a child. He took 3 showers in his entire life, apparently. So I don't know if it's a result of that. And this is a nice picture of him, apparently. He looks like somebody I knew, actually. So it made no sense. However, he did find a pattern, because he was looking for this perfect fifth. Remember I told about this perfect fifth? This is, I will be playing later on, and we'll be doing a lot of perfect fifth stuff. That's not a perfect fifth. That's because I need water. All right? That's all perfect fifths. Thank you. Remember, the perfect fifth is a ratio of 2/3. Pythagoras, in a stroke of genius, a leap of genius, was able to realize that there was a hidden pattern here, and it was the perfect fifth. It was the ratio 2 and 3. But it resulted in an equation that was able to explain the motion of every single planet. So it unified not the particular motion of one planet, but all the planets. What was it? He found an equation, discovered, not an equation is just a relationship, okay? So I know when you learn mathematics and equations are just nothing more than relationships, okay? Literally. So he found a relationship between what? How long it takes a planet to go around a star, and how far the planet is. So in other words, if you knew how long it took, so 364 I don't know what days, I forget the stuff, for the Earth to go around, you would know, you can predict, according to Kepler's law, how far the sun is from the Earth when it's closest to the sun, all right? That equation is called Kepler's law. It says the period, the time, I believe it's square. Is it square, Vicky? 2 is related to the distance, to the cube power. So he discovered the perfect fifth. That made Kepler what we call the first astrophysicist, because he was able to write down equations that predicted not the motion only for planets around our solar system, but now every single billions of planets that we have discovered at Sierra, including places. They do exoplanet research at Sierra, and they use Kepler's law, which was discovered in the 1600s, because he was doing music of the spheres. I wish I would have learned this when I was a high school student, but now it's my business to now go to the boogie down Bronx and tell them about Kepler's laws, right? Okay, we're not done yet. It gets better than that. Let me actually, full disclosure, clearly, you know, I'm going to make the case. I'm telling, there's a narrative, there's a slice of a story and a concept that I'm telling. Obviously, right, it's a way of maybe imagining our universe. And so that's what we do. We tell stories and make metaphors, right? So please, when you walk out here, don't be thinking that the universe is singing a song to you, okay? But it's amazing how far we can go with this metaphor. So these are, new planets that are being discovered by the Kepler satellite. What we want to do now, we're going to go modern on you. Or not postmodern. Postmodern is like, there's no universe, there's no space, no time, no nothing. No, nothing. But what I'm going to do now is, I'm sorry, I'm going to have to be a little bit of a professor here, and we're going to have to go through I'm going to give you some tools, some language here, so that we can then analyze our modern universe and see whether or not there is a deeper musical character to the universe. Are you all ready to go on this journey? All right, good. So the first thing, as I was telling you, is the first thing we need to understand is that actually everything I just told you really has to do with the physics of how instruments works. My instrument is just a vibrating object, and there are particular types of vibrations. You know, it can do lots of different, but the vibrations that are of interest to us are what we call resonances. These are vibrations that are particular to the shape of this instrument. So for example, there are certain types of waves that fit nicely into the instrument, and I just played for you those nice notes. Those are our musical scale. You probably learned about that as when you watch The Sound of Music. You knew it all. You knew it all when you're 6 years old. Remember that? Okay. So, but actually, it's much more interesting than that. You know, you got this. And you have the. All of those modes are contained in that one diatonic scale. And the question is, why is that? So, what's going on here? Well, those waves, those types of resonances, and these are harmonic waves. These are waves that just repeat themselves, because you can have jagged waves and things like that. That'll be a good name for a band, by the way, Jagged Waves. It's like some punk band. These simple harmonic waves, you see them there? They're identical, except that they may vibrate, more rapidly or slower than others. But the one thing they have in common is that they're periodic, they repeat, right? And they have this interesting property that when they combine, just like waves on the ocean, they crash together, it creates a very complicated looking wave. And this is at the essence of one of the most important ideas in physics and engineering, signal processing. It's called the Fourier transform. It's a simple idea that I could take simple repeating waves, combine them together, they come together, they interfere, and they create a complicated wave. But life would be boring if it was just that. Turns out the opposite could happen. I can present to you a very complicated wave, complicated as it may be, and the Fourier transform allows me to decompose it into an alphabet of simple waves of different types of frequencies. And this tool is actually super important when you do things like make a synthesizer. That's what's going on here. How can you use electronics to create the sound of a trumpet? Well, you use this idea. Or you want to do a CAT scan. So I want to actually, this is super interesting. John Coltrane and Miles Davis got very hip to this particular scale. I'll play it for you right here. That's called the Lydian scale. And this guy, George Russell, who's a theorist at the New England Conservatory, wrote a book called The Lydian Chromatic Concept. And this scale is generated naturally. It's a natural set of vibrations that's generated by what we call harmonics. You see, if I take the piano and I just play what we call these harmonics, these vibrations that occur naturally in the instrument, it naturally generates a scale. And this is one of the master scales that we use in jazz music. So in a lot of ways, the universe is really jazz is just natural to the universe. It's like one of my mentors, Donald Harrison, says, it's just natural, man. I want to talk a little bit about what, I use the word resonance. What is resonance? Well, like I said, you know, a 5-year-old kid knows what resonance is. The kid wants to go higher and higher in a swing. Yeah? So it starts off like this, but what the kid does, and I'm not talking about a goat. I know it's corny. I mean, I used to tell corny jokes. There was a joke I used to tell when I was a high school teacher. I was, you know, Mr. Fader, I have to tell you something. I have a kid. And then I pull a picture of a baby goat. And then, all right. So this kid wants to go higher. So to go higher and higher means you get more amplitude. A wave can go higher and higher and higher. How does a kid do it? Well, the kid pumps the swim every time the swing comes up. So every time the swing comes up is really a characteristic called frequency. How frequently the swing oscillates or goes back. That's a simple periodic motion. That's just a wave, if you think about it, right? Goes up, down, up, every time I go up, down. And so what the kid does, it matches, it kicks exactly at the frequency. So it puts energy into the swing at the same rate of the natural frequency. And when that happens, the swing goes higher. If the kid actually kicks the swing in between, it doesn't go up. So resonance is this idea that any kind of object that has a natural vibration, if I put energy in that's vibrating at the same frequency, that will get louder and louder. And that's exactly why the instrument is actually playing these natural resonances. And so this is exactly why when an opera singer sings and matches a natural vibration related to the size of a glass, and that vibration matches that size, the energy matches that, and there's resonance, and the glass breaks. And this is a very important key concept. So I've given you, there's no need to go to college back again for those of you who went to college already, because you've learned all the physics you need to learn. Now, there are other types of resonances that there are experts at Sierra that can teach me a thing or two, and these are things called orbital resonances. And so you have this TRAPPIST system where these orbits are resonating with each other to keep stable orbits in place. And there are musicians that actually, I wouldn't be surprised if, by the way, the band was incredible. Let's give it up to them, right? Yeah. And I think that, so in this case here, yeah, some musicians actually found the notes associated and they started jamming on this, hoping that these planets would then, you know, relay some messages from the aliens to them or something. I don't know. Good. So where am I going with this? I'm just giving you some of the basic language now, because what we now want to talk about is Einstein's universe. We want to ask ourselves, you know, can this language of music and sound be used to understand something very deep about our universe? Of course, the answer is going to be yes. The first thing we need to understand is that actually, as I said, things like instruments can vibrate, but that's not the only thing that can vibrate, actually. It turns out that this empty space that you think you're moving through, well, Albert Einstein taught us that that thing can also undergo vibration. And we know that, and we know that very well because of something called gravitational waves, which is a manifestation of the vibration of space-time, ripples of space-time. That's some of Vicky's early work. And the picture that I want to, so I like to tell my students, the gravitational force, so what makes the Earth go around the sun, is an illusion. It ain't true. There's no force. What you call the force is really just an effect. An effect. Thank you. I'm thanking myself, by the way. Of the following thing. Except space-time is some kind of invisible fabric. You should have no problem with that because you play with magnets and magnetic fields are invisible, yet the magnets talk to each other without talking, so you accept that. So there's some invisible fabric that can bend, and the picture that you should have, according to Albert Einstein, is that the sun, being so heavy, its mass warps the fabric of space-time, and the Earth moves along the contours of that warping. If you're playing a trampoline when you were a kid, right? And it will just move around. So what you call the force is just really a manifestation of the warping of space-time and objects moving along these contours. We sometimes call that geodesics. And so that's what the force really is. The extreme versions of warping of space-time for which there's no force, but things where time can slow down and where things can happen. You can spaghettify and become an alien. I know, I'm fascinated with aliens these days. According to this, there's a sense in which space-time, according to Einstein, doesn't have to just warp, it can actually expand and contract. And so Albert Einstein and his colleagues applied his equations of this warp in space-time to the entire universe itself. And what it predicted was that the universe would expand from this Big Bang, and galaxies and stars would form. This was a prediction, and Edwin Hubble, I believe he was a Chicago person, he played basketball, yeah? He discovered this law that the expanding universe predicts that the galaxies should be moving apart from each other, and that confirmed this idea that space is expanding, space of the universe is expanding. So here's a little rendition of this expanded space-time. Obviously, where I'm going and what I'm talking about here is at some point, we're going to talk about sound and music. So this is this thing called the Big Bang. I'm not going to talk about the Big Bang. Nobody knows what the Big Bang is, but we give it a name. Okay? And the universe expands, and as it expands, there's this region where it's so hot, dense, and energetic. There's no galaxies, no stars, no you, no me. I mean, I existed then. In a dream, I had a very bad nightmare once where I was in the Big Bang, and it was not cool. And then as it expands, and it cooled, and as it cooled, things coalesce, whatever this thing, we'll talk about these things, and boom, beautiful galaxies, and we're sitting somewhere over here now. And you know, humans were so lucky sometimes because, you know, as you know, the universe left us a little gift. There was a little afterglow from this Big Bang when it was very hot, and that afterglow was, for the very first time, you know, you had these electrons zipping the universe, you know, there's no atoms, right? You may have some elementary particles which want to form an atom. You know, electrons will get captured, you know, and form hydrogen for the first time. But the universe is so energetic and hot that electrons are zipping around, and at some point, the electrons form the first light elements, hydrogen, and light was released. And this was a prediction of Albert Einstein's expanded universe scenario. And it predicted this, and then physicists in the 50s went looking for this in the sky. And they found it in the late 60s. And this is a from 2017, real picture of the baby universe. Okay, this is a picture of light that took 13.8 billion years to get to us. Remember, it takes light a finite amount of time to travel, like from the sun to us. So this is light that took 13.8 billion years to get to us. And we want to now, so now is the crux of the whole thing. Now we're getting into the action. Because now, let's go back to Kepler. In Kepler's days, in the 1600s, the universe to them were a bunch of planets going out there. Now, this is our universe. This is our baby universe. And it's, as we'll see, a dot here will correspond to something very interesting, as I'll show you. But if you look at this thing here, when physicists saw this, it looked like gobbledygook to them. It was like, this looks chaotic. So what does this mean? Okay, the way you should picture this is, imagine you have this, imagine the entire universe was filled with a seething wave of fire and what we call plasma, a hot soup of particles, and combined with light. We call this a plasma. If you want to have a nice picture in your head, think about the surface of the sun. The entire universe is like the surface of the sun. Nothing else, just pure energy waving about. And this was we wanted to understand that physics and how that physics became this. Anybody have a guess what this is? Somebody's calling me to tell me what it is. I should take my phone. Somebody's, actually, who is it? I'm going to take it off. Too smart. Okay. Okay, what is this? The first thing I want you to notice, so here's a funny story. I had a friend, right? We used to hang out a lot at a cafe in the village when I was a young professor. He was this brilliant neuroscientist. He was at Princeton. I don't know why he was in New York. He should be in his lab. But we used to be drinking. And I showed him this picture, and he goes, "Where did you get these nice neurons from?" Right? Because he saw these kind of like, I didn't show him this. I showed him like, so if you take this and you zoom out, every dot is a galaxy, okay? This is now, if I zoom, this is a cluster of galaxies like our own Milky Way. So this is what we call the large-scale superstructure of our universe. Trillions of galaxies. Ours is a typical spiral like many of the other spirals out there. And so where did this pattern come from? Well, this is the here and now. Just to get a sense of scale, that's 7 billion light years. A light year is roughly in the order of trillions of miles. So I want you to think about the size scale here. But when you look at the entire picture, you see this web-like pattern. There's a pattern, and whenever physicists and astrophysicists, we see patterns, we want to understand what's going on with the pattern, right? So let's go back. How did this, so now the question becomes important. Now we have the mystery to try to understand. How did this chaotic-looking early universe, real picture, okay, this is it, become this, become us? And now we're going to talk about what this has to do with sound and music. And our way into this is to go back and return back to the physics of instruments. So when I play with my instrument, and this is a key thing here, so I need your attention. I'm going to play, obviously this is supposed to be a flute, but when I play a G here, a given note here, right? What happens is you get not one resonance, but many resonances at the same time. What do I mean by this? The note that you actually hear as a G, let me explain what this thing means, because it's super important. Every point here assigns a value of a given tone. Remember I played each of those frequencies? Every point is a given vibrational frequency, a given note. The one you hear as the G is the loudest one. This is loudness. Oh, I gave my answer away. This is the loudest. But when the instrument actually plays that one note, the vibration of this instrument generates an entire range of other vibrations, but you don't hear it as a note. You hear it as a signature, the sound of the instrument. It's what makes a flute sound like a flute. It's what makes a trumpet sound like a trumpet. So all these other frequencies that are playing at a lower frequency give basically this signature. The same way you can write the letter A with your hands and another person write the letter A, they both look at it like an A, but they are so slightly different because it's your signature. It's what makes you unique in terms of how you write the letter A. This gives every frequency here that the instrument plays and generates. And why does it do this? It reveals information about the material makeup. What makes this instrument vibrate is that it's made up of brass and other alloys. What makes a flute vibrate differently is made up of wood, not a flute, a clarinet. What makes a piano is that it's made up of strings. And so the material makeup reveals, right, how the different types of vibrations, the different frequencies, or what we call partials or formants, or there are different words for this, harmonics, different words for just different range of frequencies that the instrument generates when it vibrates. So far, so good. So actually, when you hear a note in an instrument, you're hearing many different frequencies. You're just hearing the note that you hear is the one that is the loudest. There's another thing too, that as I told you, that letter G, that G has to also do with the resonance. It has to do with the shape and the geometry of the instrument. That wave that fit in, if the instrument was shorter, it'll be a higher frequency. If it was longer, it'll be a tuba. So you have two features that instruments have. So what we're going to do now, and what was done in the 70s by a physicist, astrophysicist named Jim Peebles at Princeton University, was he imagined that actually the universe was really something that's producing sound waves. That seethe and plasma here is really a medium, like an instrument, that's actually vibrating like sound waves. And if I analyze this data in terms of waves, and sound waves in particular, then like an instrument, I should be able to learn things about the universe. For example, how big it was at that time, by finding the resonant frequency that, for example, this thing found here. But it should also reveal what the universe is made up of by looking at these other waves. That was the idea. There was no data at that time. The data took about 30 years to come. So it was a hypothesis. He worked out Einstein's equations and all that stuff. And he predicted a curve. And I'm going to show you the data. So this is nothing more than the same thing. Frequency, loudness, right, of different waves. And lo and behold, you see a resonance. You see the dominant note. This is, by the way, this is the data of this. This is the same way I analyze an instrument. I'm analyzing this data in terms of looking at waves of different sizes, and it found the pattern. It found that basically it not only is the phenomenon is actually exact. The analogy is not an analogy, it's exact. This peak we call the first peak. This peak actually predicts the size of the universe at the time that we measure this, and the rate does two things. How fast the universe is expanding at that time, and the size of the universe, and that agrees with the data, it agrees with observations. But then, if you believe this analogy, then these other waves that you see here should reveal the material makeup of the universe. And lo and behold, what you can do is look at a galaxy today and measure the amount of matter, like what we call baryonic matter, which is, neutrons and protons and things like that, hydrogen, deuterium, lithium. You can go and measure that in galaxies, and you can compare, today, you get a number, and you can compare it to this 14 billion years ago, and it's exact the same number. Vera Rubin and Fritz Zwicky looked at galaxies, and they found that galaxies have to have something called dark matter in it. So you can look at the dark matter. We don't know what it is, but we can measure its effect on how fast galaxies are rotating. And then you can look at this third peak here, 1, 2, 3. And it turns out that this third peak, 14 billion years ago, looking at these waves, gives exactly the amount of dark matter that we see today in galaxies back then. So the analogy that the universe is sort of like this instrument, and is more or less exact. Now, how much time do I have? Because I want to talk about jazz. Like 5 minutes? Okay. So, that was a nice little, I call that the classical music of the universe. But, the universe is not just expanding and big things. The universe is also quantum mechanical. So, and in fact, I teach an advanced quantum mechanics class at Brown, and I tell students, we are the exception. The fact that we are not quantum is the exception. Everything is really quantum. And how it became classical, not quantum, is actually still a bit of a mystery. Okay? And for those of you who want to hang on me later on at a bar somewhere till like 5 in the morning, I can go all into that, okay? Now, so one of my good friends, Donald Harrison, he's the NEA Jazz Master, so this is like a big deal. He played with Miles Davis and Art Blakey and others. And he has mentored countless young jazz musicians. He and I started riffing on some things. He got, he's very advanced in his playing, So he said, "Oh, you know what? I just realized that there's something about jazz improvisation that's really like quantum mechanics." And we started that conversation back in 2014, and last year we ended up actually playing some of that stuff in Kansas City. Okay, don't ask me how that went. I was just hugely intimidated, and so I want to talk a little bit about that. I want to now use some ideas of jazz improvisation to actually shed some light on quantum mechanics, or vice versa. And that's the idea here. The idea here is that you can use this analogy making between music and physics and these mysteries to shed a two-way light on each other to help us understand both of these mysteries, to help us explore these things. And so it isn't that like I use jazz music to help me with my physics, but also that like my physics and those conversations actually inform a musician as advanced as Donald Harrison to go in new directions in his playing and his creativity. So let's talk a little bit about that. So Richard Feynman really helped us understand what's really weird about, remember Feynman said, quantum, I can assure you that no one understands quantum mechanics. That's what Feynman said. Of course, as a footnote, except me. Okay? And the thing that's really weird, at the crux of why quantum mechanics is weird, and by the way, the reason why your shirt is red is purely because of quantum mechanics. Without quantum, shirt ain't red, okay? So thank the red to quantum. Okay. And the dot is red too. I don't know if it's a coincidence, but. So what you learn here, what Feynman taught us is that in the world of the big, if I throw my I'm not going to do that, throw my saxophone, it will traverse. When it travels from point A to point B, it traverses actually, as complicated as a path may be, one unique path. We agree on that, right? Otherwise, drank something too much, right? One unique path. But the thing that's weird, the crux of quantum mechanics, is that quantum particles do not do that. What a quantum particle, one quantum particle does, is according to Feynman, it considers all, I just drew 3, but all possible paths to get from point A to point B. And here's the thing that's weird. If it didn't do that, it wouldn't do this. So this comes from all these considerations. That's the thing that's weird about it. This would not happen without this weird magic going on. And so physicists, Nobel Prize winners, whatever, they debate even up till today about how to interpret this. The mathematics works very well. We use this in terms of quantum entanglement to make quantum computers one day and make them work better. It uses this idea, actually, right? That's how these logic gates work. So this works, but how to understand this, and this is where this idea of quantum improvisation comes into play. What is quantum improvisation? Well, the idea here is Donald Harrison's idea, which, with a little bit of help from me, is that, if I, in the middle of an improvisation, if I start off from, say, one note here, right, to they're all possible paths, and in every moment that can be considered. And a musician like Harrison maybe will consider and practice all those possibilities, but when they're there playing, it comes out spontaneously. Now, that's a nice analogy, but in terms of how that actually helped me in terms of how my research when I work in quantum gravity, when I try to combine quantum mechanics with space-time, because in that picture here, we're not thinking about quantum mechanics as something that has to do with probability or uncertainty. It's really, the idea may be that quantum things really improvise, right? And that's an interesting path to go down, because then you have to now bring into the idea here the question of the observer, right? How to bring in the observer into this quantum situation. So when we talk about the universe, what is the observer? So it goes down this rabbit hole, and that's the point here of this type of interplay that I've found in my career, in my crazy life, and actually how I engage with my students and how I teach and what I'm doing here. And on that note, I just want to thank you so much for your time. I'm not going to talk about the Big Bang, sorry. I'm not going to talk about the quantum multiverse, sorry. And I'm not going to talk about the cyclical universe. Thank you. The journey continues.
Thank you. Wonderful. Stefan will take some questions, a few, and then there's going to be a performance.
I will sit in with the band.
Okay. Go ahead. You can manage the questions, but then I'm going to stop at some point. Stop the questions.
Mm-hmm. Yes, anytime. By the way, I really like really bad, really crazy questions, so anything.
So are you talking about patterning that's conditioned in the field, that's conditioned in the field that maybe predates, or I don't know if dates is the word, but that exists within that arc that develops that.
You mean that pattern that I showed you there?
Yeah.
That pattern existed before we existed.
That's intelligence in the sense that exists within the structure.
So that pattern that I showed you existed before we existed. That's the first question. It evolved such that, and provide the conditions so that we could exist. Then the second question, I think, what I was hearing there is intelligence. Well, one of the people, I understand where you're going with that. One of the people that discovered this is called the cosmic web. His name is Dick Bond. he's gotten so it's into the rabbit hole of this thing, he actually thinks has to do with intelligence. But he can do what he wants. He's Dick Bond, you know? Yeah.
Could you go back to the slide for the different waves?
The slide with the different waves. Okay.
The one with the 3 peaks, that one.
Oh, you mean you mean our universe? Yes, the CMB.
Yes.
That's called a cosmic microwave background radiation. I forgot to say that. Okay.
So this might be playing into the music to physics metaphor a little bit too much, but I wanted to get your thoughts on this. So as far as I know, at least in terms of music, you can each note has its own unique natural frequency. That's the natural harmonics of each note. For example, G has its own unique natural frequency. And then you can use those natural frequencies.
Yeah, those natural frequencies is what I call a resonance.
A resonance, exactly. Yeah. And so you can use those resonances to go back and find what the original was before, even though the note G was never played.
Yeah, so let me demonstrate that to you, actually. I think this is important, but I have to get... Okay. I'm not moving my fingers, right? So all those resonances popped out naturally. Those are the natural frequencies you're talking about, right?
Yes.
Okay.
Yes.
And those are just resonances of the instrument.
So I don't know if this will connect or not, but can you use those natural the natural harmonic, the frequencies that you find at a certain point in time now, and then go back and map into, I don't know, the time of the Big Bang?
That's exactly what I showed you.
Okay.
Yeah. Thank you. You summarized my talk.
Do you think that our thought processes follow the same principle of quantum?
Okay, could I repeat that question?
The way we think,
Yes.
we don't think in a linear way.
Yes.
That's like quantum. We're not aware of it, but we consider a whole universe of possibilities to arrive at one conclusion.
Well, you know, I'm sure there's a neuroscientist here that can give a better answer. That's a really good question. That's way above my pay grade, but I appreciate that question.
So, hi, Stefan.
Hi.
That was great. I want to ask you a question maybe far afield from
That's the
science.
Associate Director of Sierra.
Yeah,
Give him a
sorry.
hand.
So you sit at this boundary between music and science, and you embrace it in your life and your teaching and everything. And
Yes.
I think one of the things that we see a lot happening today is this kind of narrative that STEM and doing science should be paramount in education versus the humanities. And I wonder if you might comment on your thoughts about the value of embracing both when we train young people to think about their lives in the world.
Yes, thanks for bringing that point up. Yes, I mean, it's essential. The arts, and by that I include music, is essential. I mean, going back to Kepler, back then all natural philosophers were trained also, even though he didn't play a lot in music theory, so he ended up using that. He was dealing with the mysterious. He drew on that as a tool to actually, that's why he wrote those notes down, to lead him to his discovery. And also vice versa. And we know, those of us who are engaged in the arts and the sciences, we know that there are elements, right, of art in the science that we do, right? There's elements of creativity and insight, all the things that I find that my artist friends feel joyful about. We find it in the science that we do. And also vice versa. There are elements that are, of practice, of discipline, all these things that happen, even logic that happens in the arts as well. And there's a nice overlap between those two things. And it's important for them to be in conversation with each other to amplify each other.
One more question?
Hi, thanks so much for the presentation. It's really fascinating. And I always find the picture of the ancient universe very fascinating. If you could go back to the slide, it's the oval, which is, I guess it's like microwave radiation.
Yes.
I think it's more a technical question on how they took that, and I'm guessing it's a special telescope, but then how did they know where to point, and how big is the picture? Is it just a part of the old universe? Or?
So this is a space satellite, and basically what it's doing, it's basically, it's covering the entire sky. It's basically taking a picture of every point in the sky, right, and collecting that. And what this really is that, imagine you're a chicken inside of an egg, and you're looking out, and all this is really just like a projector, the same way we project the Earth into a flat surface, but this is the entire sky. Thanks for bringing that up, all right?
So this is the entire universe from our perspective, basically.
Yeah.
Wow, thanks.
I should have said that, thank you. That's why questions are important, right? Okay.
Take one more question.
These are great questions, actually, hard questions. Oh, good, good. That answer is known, actually. That frequency is actually, where's my thing here? Where's my, I'm pressing the wrong button. So. It turns out that we know that frequency. It's the A note. It's exactly 440 hertz. 50 octaves below middle, because it's the universe, right? But that frequency is known. The one here, that's A. So the universe is actually resonating at that note. Okay?
All right, so thank you, Stefan.
What are you playing first?
And now, help me welcome again the Star Eyes Initiative Band tonight, and they're gonna perform with Stefan together.
You guys sounded great, by the way. Make sure. Oh, let me get a two with you guys. Play me your C. In fact, one of the most, they call him a space cadet. Physics-oriented jazz musicians is Wayne Shorter, and this song is a Wayne Shorter tune. So let's begin. We'll start with you, right?
you.